Welcome, and thanks for watching this online training video. My name is Craig and I'm a Processors and DSP engineer at Analog Devices. This module is focused on migrating from SSL 1.0 in VisualDSP to SSL 2.0 in CrossCore Embedded Studio. In this module, we will provide an overview of the process for migrating from VisualDSP and SSL 1.0 to CrossCore Embedded Studio and SSL 2.0, providing a feature comparison and overview of the significant changes, together with a simple UART demo. This is followed by a live demonstration, porting a simple VisualDSP project that uses the system services and device drivers to CrossCore Embedded Studio. Using a simple audio talkthrough application that uses the SSM2603 codec driver, we will remove redundant services that are no longer present in SSL 2.0. This involves removing include files, global memory definitions, and API calls. These memory allocations for the system services will be replaced by memory definitions for individual device drivers, before replacing the old Device Manager API with device-specific API calls. Finally, the callback function will be modified to be polled periodically. In this next section, we will be looking at the differences between the system services and device drivers under VisualDSP++ and the new system services and device drivers model offered in CrossCore Embedded Studio. This table offers a high-level overview of the changes. Instead of a central device manager service as we had in VisualDSP, the concept has been removed, providing device-specific API and resource management. The Central Interrupt Manager service has also been removed in favor of the devices managing their own interrupts. Along with this, we have removed the concept of primary and secondary interrupts. Callbacks are present in both SSL 1.0 and SSL 2.0, however, callbacks are, in general, discouraged. For the reasoning, I recommend reading Chapter 5 of the Device Drivers User's Guide. Deferred callbacks have also been removed in SSL 2.0. There are non-blocking buffer transactions, however. As with other services, there is no longer a central user-controlled DMA manager service. Again, the device drivers manage their own DMA requirements. The power management service has been simplified to focus on core and system clock configuration only. The external bus interface unit service, which interfaces with SDRAM, Flash, and SRAM, has been removed, as providing a generic API for EBIU settings over our wide range of processors was counterproductive to simplifying the API. The EBIU should be configured through direct access to the registers. The flag service is now the general-purpose I/O service. The system services and device drivers in CrossCore Embedded Studio are compliant with the Motor Industry Software Reliability Association standard, MISRA-C 2004. Finally, in SSL 1.0, it was necessary to calculate the memory requirements for your application at a global level to ensure various management services had enough resources. This is no longer the case in SSL 2.0, with the removal or modification of most of these services. The device drivers provide memory size definitions that can be used instead and include the necessary resources for DMA, etc. In summary from the previous slide, the device management service has been removed, as has the deferred callback manager, DMA manager, interrupt manager and secondary interrupts, and the EBIU service. The major changes that have been made are that users do not need to pre-calculate the required resources for their application. Callbacks are no longer the default, nor are they recommended. We have greatly simplified the power service and replaced the flag service with a GPIO service. The device drivers are now MISRA compliant. Perhaps most notably, due to the removal of the centralized device manager, the device drivers all have their own device-specific API based on the common low-level device driver API and manage their own resources. What this means for porting an application from VisualDSP to CrossCore Embedded Studio is that there are a few necessary steps in making the transition. You must remove the API calls for the removed system services. You must remove any included header files for these removed services. You must add memory definitions for individual device drivers and remove the global memory definitions for all of the system services. Device Manager APIs should not be removed. These should instead be modified to use the equivalent command from the device-specific API. And you must modify or remove any callback functions. Here is a very basic example that demonstrates at a high level the principles for porting an SSL 1.0 project into CrossCore Embedded Studio with SSL 2.0. We have three separate includes in SSL 1.0. The first is the services.h header file, which in turn includes a header file for each of the services: the interrupt service, deferred callback manager, DMA manager, etc. We then have an include for the device manager, and finally the include for the UART device driver. In the new system services, we need only the UART device driver include. These are all of the SSL 1.0 handlers for the system services and device drivers, as well as the memory allocations for each service. We must pre-calculate how many of each we require so we can issue enough memory to each service. A common issue people hit with SSL 1.0 was not editing these values to allow for additional device drivers when augmenting an application, or not allowing for underlying low-level device drivers required for a higher-level device. For example, the SSM2603 codec actually requires memory for 3 device drivers, as it has an underlying Sport and TWI driver, as well as the codec driver itself. In SSL 2.0, we simply provide a handle for the device and the memory for the device through the size macro provided by the device driver. In SSL 1.0, it was required that an application initializes each of the system services. Here you can see initialization calls for the interrupt manager, power service, deferred callback manager, DMA manager, device manager, and a call to open the deferred callback manager. In SSL 2.0, most of these services have been removed, as detailed earlier. In this particular example, of all those calls, only the power service initialization is still required. Next is the device driver itself. Through the device manager APIs, we open and configure the device, enable transmit, and then submit a buffer. There is a lengthy configuration table in the middle of all this code, used together with the ADI dev control call to configure the device. These tables provide a means to configure a number of aspects of the device through a single ADI dev control call. Instead of the device manager API, each device has a specific API, so the ADI dev open call has been replaced by the device-specific ADI UART open call. The configuration table and ADI dev control call are replaced by individual APIs to set the baud rate, set the configuration, etc. Again, the ADI dev control function makes way for a device-specific API call, which should look similar enough to be straightforward. Finally, the buffer is submitted through an ADI UART read call, a device-specific API that replaces the ADI dev read API from the device manager. That example gives you a brief overview of what is involved in porting legacy system services and device driver code to CrossCore Embedded Studio. We will now cover these steps in more detail as we go through our live demonstration, porting a VisualDSP project which uses the SSM2603 codec device driver to CrossCore Embedded Studio. This demonstration will take a simple audio talkthrough example from VisualDSP that makes use of the system services and device drivers, and provide a practical demonstration of the steps necessary to import this project into CrossCore Embedded Studio and make use of the SSL 2.0 API. The CrossCore Embedded Studio API is very different from the one in VisualDSP. Porting, however, is relatively straightforward. Go to File, Import, Expand General, and select VisualDSP++ Project. Browse to the project directory and then select the DPJ file. When the import completes, you can view the report. Close this. Open the system.svc file and add the pin multiplexing add-in. Select Yes when offered to add the initialization code and call. Go to the pin multiplexing tab. Expand Port 0 on port G and check the following options. Close the system.svc file and save the changes. The first step I would take is to update the included files. All of the includes at the top, apart from ADI-initialize.h, which was added by the system builder a moment ago, and stdio.h, can be removed. That includes the codec driver include. This file name is different in SSL 2.0 as it's a generic SSM2603 codec driver, rather than one specific to the BF52X variants with the on-chip codec. Include string.h also, as we will be using memset later. The next step is to define the handle and memory for the device driver. As part of this process, we also need to get rid of the now redundant defines for the DMA and device manager handles, as well as the definitions for the number of services, memory for each service, and so on. This is a big chunk you get to remove and demonstrates one of the biggest benefits of the new model. You don't have to calculate all your memory requirements up front. This whole block can be removed and replaced with just a handle for the SSM2603 device and the memory for the device driver. We also need to remove the power management service configuration table, as the power service is simplified to only set the core and peripheral clocks. The same goes for the TWI configuration information, as we will not be directly using the TWI device driver. Instead, we will be configuring the TWI through the SSM2603 device driver. The ADI SSL enter critical definition is also not required. We have defined our SSM2603 handle earlier, so no longer need the BF52XC handler, nor do we need these exception handler prototypes. The callback prototype can also be deleted, as we will not be using callbacks in SSL 2.0. Finally, remove the exception handler functions here. The buffers in SSL 2.0 are handled differently also. There is no longer the need for the SSL-specific ADI dev1d buffer types used here, so the whole section for the codec buffers can be removed. We will keep the define for the number of samples, but rename it to buffer size. Align the buffers using the align pragma. Instead of defining the buffers as we did before, we will define 4 static unsigned int buffers of size buffer size. Copy this and edit to define our 2 input and 2 output buffers. The top of the source file is certainly looking a lot cleaner at this point. Again, this is largely through the removal of a lot of the memory management and management services that were present in SSL 1.0, but the simplification of the buffer management and other services also played their part. The next stage is to start fixing some of the API calls. Within the main function, we must remove the redundant function calls for all of the services that are no longer required in CrossCore Embedded Studio. These can be removed and don't need anything else added in their place. We will leave some of the calls, such as the ADI dev control calls, as these have parallels in the new API that we can convert them to. Remove the interrupt service initialization call, the deferred callback manager initialization call. Also remove the DMA manager initialization call, and the flag service initialization call. The flag service is now the GPIO service, but is not required for this device driver in CrossCore Embedded Studio. The device manager initialization call can also be removed. The ADI DCB open call to open the deferred callback manager service can also be removed, as can these hook functions for the exception interrupt and hardware error handler. Ignore the ADI dev open call for now. We will change this to the device driver specific one, as we will also do for the ADI dev control calls. Again, as we are not using the flag service, we don't need the open, set direction, or clear calls here. These have similar API in SSL 2.0 under the GPIO service, but as they aren't necessary for the SSM2603 driver, they are just being removed. Take a look at the GPIO service documentation if you want to see the valid API. Still within main, we can remove the config bf52x-c1 table, as this is not necessary either. We can take care of these settings elsewhere. In particular, we will use the setVolume API from the SSM2603 driver to set the volumes. This code contains a number of checks on the value of result, which use enumerations that are now invalid. We can change all of the ADI dev success conditions in the result checks to 0. If you want, you can change these to specific enumerations such as ADI power success, ADI SSM2603 success, etc. But for brevity, I will just change all of these to 0, as this is the universal success value within the device drivers. We now need to modify the power service call. As we don't have that power settings table due to the simplification of the power service to only allow clock configuration, the ADI power init call needs to be changed to use numeric values to set the clock in to 25 MHz, the core clock to 500 MHz, the peripheral clock to 125 MHz, and the VCO minimum to 60 MHz. In the ADI dev open call, we need fewer parameters as the central device manager is no longer used. We don't need to pass a device manager handle or entry point as there is no device manager service and the open call is device specific. The first parameter is still the device number, so does not need changed, but the second parameter is the device driver memory. The third parameter is the memory size, and the fourth parameter is the device handle, which just needs to be modified here. There is no DMA manager, no callback function, or deferred callback manager either. We also don't set direction here, so remove these additional parameters. Finally, change the ADI dev open call to the device driver specific API call, in this case ADI SSM2603 open. Next, there are a number of calls to ADI dev control. This API takes a device handle, a command, and a command table. Each of these commands, where they are still relevant, have been replaced with a specific API call. For example, the ADI bf52x-c1 command set TWI global address has been replaced by ADI SSM2603 set TWI device, which takes a TWI device number and a TWI hardware address. Similarly, the set sport device number command will be replaced by a call to ADI SSM2603 set sport device, which takes a sport device number and a sport operational mode, either transmit, receive, or both. The register field table write command can be replaced with a call to the ADI SSM2603 set register API. In this case, we'll just write all zeros, as this gets the device to reset itself to default settings. You can use individual calls to set register to configure the registers on the device to specific values. As with the other ADI dev control calls, the sample rate command has a matching API. So replace this command with a call to ADI SSM2603 set sampling rate, using 44.1 kHz sample rate for both the ADC and DAC and the 12 kHz MCLK. The next section of code in the application configures the buffers, sets the data flow method of the device driver, and submits the buffers using the ADI dev read and ADI dev write functions. The read and write APIs still exist, but are blocking operations, halting any processing until a device driver completes the transfer. As this example used deferred callbacks, we need to use the non-blocking operations submit buffer and get buffer. Use submit RX buffer and submit TX buffer to provide two buffers to your device. These will be used as ping-pong buffers automatically by the device. So you have to submit two RX buffers and two TX buffers. First, initialize them to 0 using memset. The ADI dev control call to set dataflow method is no longer required, so remove this. We will replace this in a moment. Now, replace these ADI dev write and ADI dev read calls with the submit buffer API. The device handle is still required, though we have used a different name, so need to change that. The ADI dev 1D buffer is no longer used, we just need to provide the address of the first element in the buffer. These API also take an additional parameter, the buffer size. Repeat that call for the second receive buffer. Similarly, replace the ADI dev write call with a call to submit TX buffer. Add code to check the result, then repeat to submit the second transmit buffer. We removed the setDataFlow method call, and the setDataFlow command to enable the transfer is also gone. Instead, you need to enable and disable transmit and receive independently with ADI SSM2603 TX enable and ADI SSM2603 RX enable. As mentioned earlier, we also need to configure the volume, as that was originally taken care of through the ADI dev control call with the register field table write command. Instead, use the set volume API. This needs to be issued 4 times. A call for each of the left and right channels of the DAC, and a call for the left and right channels of the ADC. Back at the top of main, modify the definition of result to a uint32t data type. Remove the definition for I, response count, and sample rate. That's the configuration done and the main function complete. Next, the callback function needs to be modified. As mentioned earlier, we discourage using callbacks, so this function won't actually be a callback. Instead, we will call it periodically from a loop in main. The first thing we do is change the function prototype to take no parameters and to return an ADI SSM2603 result type. I'm also changing the name to SSM2603 process audio. The declarations for I and the ADI dev1d buffer are not necessary. We will also change the source and destination pointers slightly, as they are used differently in this case. The function returns an ADI SSM2603 result, so add this at the start of the function and set it to success. The function isn't a callback, so it doesn't need to switch for the different events. We will be polling it rather than triggering it through events such as completed buffer. So, remove the switch code. I will also quickly correct the indentation. Replace the code to get the address of the processed buffer with two calls, one to get the receive buffer and one to get the transmit buffer. What these calls do is reclaim one of our ping-pong buffers which has been processed by the device. If the transfer hasn't completed, these will become blocking calls until the transfer has completed. The example could be extended to use the peek functions offered by the device driver. Is Rx buffer available and is Tx buffer available? If the buffer is not available, you could then exit the function and continue with other processing, rather than blocking until the buffer is complete. The next few lines get the addresses of the buffers, but this isn't really necessary as we are no longer using ADI dev1d buffers. Instead, just check that neither of the buffers we obtained above are null. The processing in this example is very simple too, just copying from one buffer to another. Replace this code with a call to memcopy. We need to add some more code after the processing in this SSL 2.0 project, as we need to resubmit the buffers to the device through the submit buffer API calls. First, add a call to the submit Rx buffer API and check the result. Then add a call to the submit Tx buffer API and again check the result. Set the two buffers back to null and return the result in case there is a problem. Back in the while loop in main, add a call to this function and check the result. And that's it. The project has been converted from SSL 1.0 to SSL 2.0. Note that the source file that was over 400 lines long in VisualDSP is now around 180 lines long. And this concludes the training module on the system services and device drivers for CrossCore Embedded Studio. Here are a few links where you'll find more information on the various topics covered throughout this video. Visit the Analog Devices video channel for our other CrossCore Embedded Studio training videos. I would also recommend the CrossCore Embedded Studio help and the code sketches offered in CrossCore Embedded Studio via the Browse Installed Examples option on the CrossCore Embedded Studio welcome screen. Thanks for watching.